which we said I was defined as dq over dt. And this is the current as we know it. dq dt. Now, one thing about this is that this big I, it's positive charges, okay? So the current that we know, big I, is the flow of positive charges. Whereas the electron current, it's the flow of negative charges. Now, another thing that we got out of this was the idea of current density. And current density is given the symbol J, and it's I over A. So it's whatever our current is divided by our cross-sectional area. And by the way, it was also equal to N sub E times big E times VD, like that. I think that's right. Am I leaving out an E on that again? I mean, yeah. Times. No, I think it's good.
Dr. Glazer,
Yes.
is that a negative or is it just a triple equal sign?
This right here,
Yeah.
it's a triple equal sign. Defined as.
Okay, got it.
Triple equals.
I was just like,
Now the thing about the current density is it tells you how much charge is flowing through a wire, but if you have, for instance, the same amount of current flowing through a fat wire and the same amount of current flowing through a skinny wire, which one has a higher current density?
Skinny wire.
The skinny wire, because it's got a smaller cross-sectional area. So it's a way to distinguish, even though they're carrying the same amount of current, this may be something of interest, right? Smaller wires tend to heat up more, and the reason why is because they have a higher current density, okay? Given the same amount of current. So this idea of current density, and I could have some wire that starts off being this big right here, and it has some cross-sectional area, like this, and maybe it tapers down to some little wire like this with some smaller cross-sectional area, and I could ask you to compare the current densities, okay? So that's an idea there. Okay, now one thing about current though, because charge is conserved and current is just moving charge, that means we have conservation of current. And from this, we have two different things of importance. One is that anytime you have one wire, no matter what is on that wire, be it resistors or maybe it's a battery, or whatever it is, if it's all on the same wire, then it's going to share current, okay? So maybe we have some I going out this way, and we have some I going in this way, like that. Well, in any case, I in is going to equal I out if it's the same wire, which is why we can separate off all of our different little currents when we go to use Kirchhoff's laws. Now the loop law is different, right? That's going around different loops, potential loops, but anytime you have one wire, it's going to share one current. So this is an example of that. Also, at junctions, current has to be conserved. So if you have I in going this way, and we have I out 1 and I out 2 going this way and going that way, I in equals I out 1 plus I out 2. In fact, the sum of all the currents going in has to equal the sum of all the currents going out. Okay. Last thing from this chapter. Oh no, I think that was the last thing from that chapter, maybe. I think that's the last thing from that chapter. Okay, the next chapter, which we don't have that much time to go over, but it's circuits. Circuits are going to be on there. There's a few things that I want to point out about the circuits chapter, besides the obvious Kirchhoff. You got me. It's because I tried to erase the big picture and it did not like it. I'll leave it. I'm not going to fuck with the big picture.
Have you found another big eraser like the last classroom?
No, that was fantastic though. I would carry one around with me, except for they're full of frickin' chalk. It's messy.
Your shirt can attest.
You wear black clothes around a chalkboard and you just realize how much chalk that you have on you. Okay, now one thing to remember is that power equals IE, okay? So don't forget the power. The power, okay? This is power produced by a battery. If you had some resistor, the power dissipated by the resistor would be equal to I delta V. Okay, that's the power dissipated by a resistor. We also have Ohm's law. Remember what Ohm's law said, right?
No.
Shit. V equals I times R. That's Ohm's law.
Oh. Yeah, that one.
Ohm's law. Okay, so that tells you the relationship between the voltage across the resistor, the current through the resistor, and the resistance. Okay, this is all more recent stuff. I'm running out of time. Damn.
You could just exclude this part from the test.
No.
Or we could have only Kirchhoff problems.
Yes.
Only Kirchhoffs? Well, I liked all those. Remember the problems that I put, I gave you guys in lab that were like, which light bulb is going to be brighter and dimmer? Yeah, I'll probably do some of those.
Conceptual stuff like that.
From this chapter. I'll probably put some Kirchhoff's laws stuff from this chapter. Basically, it all builds up to circuit analysis. So, and that's using Kirchhoff's laws. If you do the linear analysis all on your own, I will give extra credit. If you do it on a calculator, you'll get full credit. But if you build a matrix and you solve the matrix, that's worth extra credit. Yes?
If you're solving a matrix and
Pretty easy.
Okay, that's a good question. So let me just see if there's anything else. You guys know that resistors in series, you just add them up, right? And resistors in parallel, you add them as 1 over the resistance. I'm not going to go over that. But
Can you give us an example matrix that we could do by hand?
you want me to just do it, bust out an example matrix real quick?
I don't remember.
Yeah, I don't want to do that either. But I do want to get to her question, which is, let's say, so the example circuit we had before looked something like this.
I remember I do matrix.
Let me simplify this a little bit.
Ultra YouTube video for like 2 minutes. Didn't you give us the same one before?
I don't know, something like this. So what you're gonna do is the first step in doing these problems is choosing the direction you think the current is going to go. And there's only one where there's 2 rules you have to follow. What are the 2 rules you have to follow?
Junction.
That's right, at the junctions it can't go all in or all out. What's the other rule you have to follow?
The loop.
Each wire has the same current all around the wire. So in that case, you say, okay, well this wire right here, I'm going to call that whole thing I1. This wire right here, I'm going to call this I2. And then, let's see here, this wire right here, I'm going to call this I3. So you're going to just choose based on those rules, right? The only thing is you can't have all the currents coming in together, and you can't have all the currents going out together. That's the only rule, right? Then when you solve the matrix, let's say you got something like I1 equals 0.125 amps, I2 equals negative 0.135 amps, and I3 equals negative 0.02 amps. Okay? Well, all that means is that, oh, that can't be. If you get that, then you know you're screwed up, because now we have violated the second law, or the first law. Okay, let's just say one of those guys came out negative. Okay, but what the negative current means, all it means is that when we chose these to begin with, we chose this in the wrong direction, and for our physical circuit, whatever the voltages and batteries and resistors ended up being, the current is actually going in the opposite direction. Okay, that's all it means. There's nothing wrong with that. In fact, as long as you clearly define your currents in your loop, and I look at it, it's pointing in that direction, you get a negative current,